Lecture 29 of Physics 1401. So let's shift gears completely. We are now going to talk about fluids. So what is a fluid? We are going to define what a fluid is. We will define the pressure and its units in the fluid. We will see how pressure in the fluid is related to each other. We will see how pressure is measured, and then we'll see what the differences between absolute and gauge pressure is. So first of all, we have to define what a fluid is. A fluid is basically material that can flow, and it can take the shape of the container it is in. So this includes both liquids and gases. And at the first glance, a liquid and a gas look different. However, they are basically very similar because both in liquid and gases, the atoms move relative to each other and there is no fixed arrangement between the individual atoms. And this is completely opposite to a solid where the atoms are in an ordered arrangement and the distances are fixed and the directions between the molecules are also fixed. So this is completely different. In a gas and in the liquid, you have the atoms moving, and in the solid, you do have the atoms somehow put in place and not moving and are fixed. So this is a funny example out of Germany, where at some particular events, people are drinking beer out of these beer boots. So the liquid beer is going to float and fill the entire funny shaped glass. So what is now the difference between a liquid and a gas? We have seen both are flowing, so they behave similarly. However, in liquids, we do have the distances between the atoms very, very small, and in gases, we do have them very, very large. So this is the difference. And this is now a conclusion of these differences. So if you have a solid, it holds its shape and it has a fixed volume. If you have a liquid, then it fills the container it is put into. It has a free surface and it has a fixed volume. So fixed volume is the same for solid and liquid. However, the liquid flows and is not filling the entire box here. And this is also similar to the solid. If you now have a look at the gas will fill the entire container. The molecules are moving. The molecules are also moving here in the liquid. You have the volume of the container, and here you do have the volume depending on how much you got from that liquid. And if you have a gas, or also if you have only a very small amount of gas, the gas will fill the entire container. So these are the differences between solid, liquid, and gas-like. And you see there is a couple of things which are common. The common is that the molecules move and that they are filling basically the shape of the container you're putting them in. So when we talk about fluids, we also need to talk about density because we are going to need this quite often now. The density, as we have seen previously, is defined as delta M over delta V. So mass divided by volume. You can also do it as a dm over dv, or if you have a particular object in mind, it is just the mass of the object or the mass of the fluid divided by its volume. And then the unit of the density is, of course, here we have kilogram, and this is cubic meter. So the unit of the density is kilogram per cubic meter. And what we also need to know for liquids, not for gases, for liquids the density is constant. For gases, the density is not constant. So liquids have a constant density. So I have a look at some of the densities of various materials. So if you're looking at interstellar space, we get the density here measured in kilogram per cubic meters of 10 to the minus 20. So this is very, very low. When we're looking at air at 1 atmosphere and 20 degrees Celsius, we have 1.21 kilograms per cubic meter. Ice of water, 917. Water at 20 degrees, 998. Seawater a little bit higher than sweet water because there is the salt in it, so it's 1024. Mercury, a liquid we are very familiar with, which is metallic and is relatively heavy, So heavy is because it has a high density. So this is about 13,000. And when we are looking at something extreme, which is a neutron star, we are dealing with a density of 10 to the 19. So you see, you have a huge span of orders of magnitude also available for densities. Now, when we have a fluid and we are going to put an object into the fluid, we will see that the fluid exerts force on any surface on the object, and the magnitude of this force does not depend on any orientation of this surface of the object in the liquid. It just depends on the area the object has. And now we are going to define the pressure, and this is abbreviated by a small p, by the ratio of the force in the area. So the pressure I'm experiencing is the force acting upon an area A. And this is the magnitude of the force, and it's not a vector entity. So this is the magnitude of the force divided by an area. So I'm dividing a scalar by a scalar, and therefore also the pressure is a scalar. So it is not a vector. And the unit of the pressure is Newton divided by square meters. As you can see from the definition equation, force is measured in Newton, the area in square meters, so we have Newton divided by square meters. And this unit has a special name. The special name is Pascal, and Pascal is abbreviated by PA, capital P, small a. Where that Pascal unit comes from, we will see in a second. So I have made an example here for you. So if the pressure in the heel, I have considered a 50 kilogram woman, and she is distributing her weight half onto the toe zone and half onto the heel. And I calculated the force which is coming out of this distribution. So the 50 kilogram person, we just take half of the person's mass and then multiply it with 9.8 meters per second square, and then we get 245 Newton as the force which is going to be applied onto these heels. So what I need to calculate is the pressure by taking that force I just calculated from the 50 kilogram person divided by the area which it is put upon. So I have to calculate 245 Newton divided by the area. So when I take this heel here, 5 times 5 millimeters square, this is that very small one, I get about 9 million Pascal. And this really here is a weapon. So when I take this heel here, which has roughly an area of 1 times 1 centimeter, I still get about 2,500,000 pascals. And then when I take that kind of heel here, whereas everything is very, very flat, I get in the order of 50,000 pascals. So this is the difference by having the same person standing on different shoes, what the pressure in the heel would be when they are walking on these various kind of shoes. Now, where does the unit Pascal come from? Well, it comes from this gentleman here who lived in the 17th century. Blaise Pascal did early work on fluids and clarified the concepts of pressure and vacuum, and then generalized the work which had previously done with Evangelista Torricelli. And this person here, Evangelista Torricelli, you also have probably heard that pressures are going to be measured in torr. This is true, and that abbreviation torr comes from the word Torricelli, which is another person. And this is the relationship how 1 atmosphere, which is also not an SI unit, is going to relate to the unit we are going to use, Pascal, and millibars and torr from Torricelli. So this is the translation for 1 atmosphere into the SI unit we are going to use and into the unit of millibar and torr. Just if sometimes something like atmosphere or so pops up, you can convert it into the SI unit. Now let's have a look at pressure and fluid and how it depends on the height. So everybody knows, and divers in particular, that when you are diving, the pressure increases with depth. And climbers also know that the pressure is going to decrease with increasing altitude. So if you have to go up to Mount Everest, you usually need oxygen because there's not enough oxygen anymore, not enough pressure in order to hike up in these heights without extra pressured air. So let's consider this tank here of water, and we are going to look for this volume element of water, which has a height h and has an area of A, and this is being placed down here in our tank. So this is where this water element is located. So, and we also know when we have located this, there is no net force on this piece of water because it's not going to move either upwards, nor downwards, nor left, nor to the right. So let's have a look what kind of forces are going to be involved. So first of all, we know that this object water here, that cylinder water obviously has a weight. So that weight can be easily calculated. It's the mass of the water element times g, and this is the density of the water times the volume of this particular cylinder multiplied by g. So I'm going ahead and rewrite the volume. So I keep my rho, and then I'm going to use the area and then the height, and this gives me the volume A times the difference in the heights. So this is here this is the height of the object, the difference into these two positions in the y direction. This gives me the volume, and then I do have G. So this is one of the forces which is obviously pointing downwards when I would draw a free body diagram. However, this piece of water is in equilibrium. Equilibrium means it's neither sinking nor rising, nor going left nor right. So that means I am somehow missing an upward force in order to stabilize that from sinking. So that means I do have to use the pressure, or the pressure is the reason why that piece of water is not sinking. Okay, so just imagine we have at position y1 and y2, we have the pressures P1 and P2, and then we do have forces on the surfaces of our cylinder, which is the force at the position y1 is P1 times A. It's the force pointing downwards. And then, of course, we do also have the force at the position y2, where we do have P2 times A pushing upwards. And in addition, as we have described in the previous slide, we have the weight of the object, which is also pushing down. So these are the three forces which I have and which I would have to put into my free body diagram. This is the weight going down. This is the force P1A pointing upward, and then I have the force P2A pointing downward. And these need to be equal, so that means all the downward forces need to be equal the upward force in order to make that piece of water not sink or rise. Okay, so that means in equilibrium we need to have that the pressure P2A, this is the one down here, is going to compensate both the weight and the pressure which is coming from the surface. And this is what is written down here. So P2A, this is the force pressuring applied here at Y2, and this is the force applied up here plus the weight of the object. And I can now go and divide by the area A here in this equation, and then I'm ending up that the pressure P2, which is the pressure down here in the water, is the pressure P1, this is the pressure right here, plus rho times G times the difference in this position. And the difference in this position is nothing else as the height of this water segment. So I can rewrite this equation by that the pressure I'm finding somewhere in the depth h below the surface is the pressure P0, this is the pressure up here, times rho times G times h. And in order to do so, I'm going to move basically my zero line here to the position of y1, so that I have the position, that I have the pressure at the surface of the water being the one at the position y1 here, and then I can just replace this with h, the depth under the water surface. Now let's have a look at the unit of this one. So this is measured in Pascal, and this of course is measured in Pascal too. So let us have a look whether this part of the equation is also delivering Pascal. So I have to put the units of my density in here, which is kilogram divided by cubic meters. My gravitational acceleration is meters per second square in its units, and height is measured, or depth is measured by meters. So when I already have done this part of the equation here in red, because this delivers Newton, so I can put Newton here in the denominator, and then the meter to the 3 with this meter is going to be a meter squared in the denominator, and this is indeed the unit of Pascal. So that all makes a lot of sense. We don't have to double check this again. So this equation holds for any shape of any container, this equation here. So that means when we have a look at Hoover Dam or having a look at the Kaprun dams in Austria, it's not the amount of water which is basically stored behind these dams. It's only the height of the dam which describes the pressure which is down here below at the bottom of the dams. So this is very important. It's not how much water is behind there. It's just how high the dam is. So in order to build a dam, you only need to know how high it's supposed to be in order to calculate stability criteria, and not how much water is actually being stored behind it. So now we also have to see how the atmospheric pressure comes into play, because we do have atmospheric pressure here, and this atmospheric pressure is pressuring down onto the water surface. And now we have drawn this water element right there, as we have now defined this equation, that our value y1 is directly located at the water surface. And then when we are measuring the pressure down here, this is the depth in the water, so this equation applies. So when we know now that we do have an atmospheric pressure here, then very easily we can see that our P0 here is nothing else than the atmospheric pressure which is here within the air. And how can you interpret then this equation? Well, this is nothing else that the pressure down here is made up out of this part here, which is due to the weight of the column of water plus the atmospheric pressure, which is pressuring onto the water from the top. This is how you can do the interpretation of this equation when we use this particular idea that we now have our water column sitting directly with its top at the air-water interface. So let's have a look at a scuba diver. So we have a scuba diver who is going to go down into a depth of 30 meters beneath the surface of the ocean. So the diver is in salt water. The density of salt water, as we have just seen in the table, is 1,024 kilograms per cubic meter. And the atmospheric pressure is 1,013 hectopascal. So now what is the pressure at the depth of the scuba diver? So let's put the numbers in. So the pressure at 30 meters is the atmospheric pressure times rho times g times h, the equation we just derived, and we are putting our data in. So the atmospheric pressure is here, 1,013 hectopascal. Hector is 10 to the 2. And then we have 1,024 kilograms per cubic meter was the density of the seawater, our gravitational acceleration, and then the depth was 30 meters. We already have seen that this here really is delivering Pascal, and when I put the numbers in, I get 4,024 hectopascal. Now we can have a look, when we look at 1 centimeter's surface of the diver, how much force is acting on 1 centimeter square of the diver's body. So we take this pressure definition equation into consideration and just put in what we and solve with respect to force, and then just put in what we have just calculated. So the pressure here is 4,024 hectopascal, and this times 1 centimeter square, and then that gives us 40.24 Newton on each square centimeter of the body of a diver. So when you're going to scale this up, depending on how large the diver is, you can see there is a lot of forces acting on the diver and pressuring this person together. Okay, Now, when we talk about pressures, we also have to talk about whether this is the total pressure, so the absolute pressure, or whether this is a gauge pressure. And the gauge pressure is something where you are going to measure the pressures, and many of these pressure gauges only measure pressure differences, and they are measuring gauge pressures. So it's not the absolute pressure which is actually there, it's the difference between the pressure which is available and, for instance, an atmospheric pressure. So that means, because we are talking now when we have gauge pressures for differences, these differences or these gauge pressures can either be positive or negative. So an example for a positive gauge pressure is the pressure in a tire. So obviously you have a higher pressure in your tires in comparison to the atmospheric pressure outside. And the negative pressure, also with respect to the atmospheric pressure, would be the pressure in your lungs when you're going to use a straw and you're going to suck on it. Then you do have a negative pressure. So now let's have a look at an example where we have a U-tube. So this is a U-tube here. It's called like this because it has the shape of a U, and it is filled with partially with oil and then partially with water. And because the oil and the water have different densities, you do not have an equilibrium that you do have the oil-water interface being here. So this is shifted to an unsymmetric way because the two densities here are also unsymmetric. They are not identical. So when you have that, you can define now the height of the water column above this line where the oil-water interface is, and you can define this as L. And then the difference between the water-air interface and where the oil-air interface is, you define as D. So what are the data given? So we have a U-tube which is open on top. So on both sides it's open. So that means on both sides we do have atmospheric pressure available. And it contains two different liquids. The water is given with its density, 998 kilograms per cubic meter. And the oil, we have an unknown density. And we have given the height L here. This is the height between the water-air interface and the interface here between the water and the oil. And we also have D given, which is that distance here. And we are asked for the density of the oil. So the first thing we have to figure out is that the internal pressure in this U-formed glass object is that the pressure right here along this line is the same as over here. If the pressure would not be identical, so if the pressure would be higher here, then the oil would move to the left. If the pressure would be higher here, then the water would move the oil upwards. So in order to have this at an equilibrium and this line here not moving, you need to understand, you need to know that the pressure here and the pressure here along this line is exactly the same. Okay, so when we know this, we can write down that the internal pressure here at this line is now considered from the water side. So the internal pressure right here on the water side is the atmospheric pressure, which comes from this because it's open, and then times rho of water, gravitational acceleration, and then the height here, which is nothing else than L. So H here equals L. This is the equation we can use. Now, we also need to have the force which is coming through to that on the oil. So the force which is pushing up, because we do have this on that hand side, we have the same pressure over here, which is pushing the oil upwards. So we can write that this force pushing upwards is the internal pressure we have calculated here times A, which is the area of that tube. So, and this is nothing else than A times P atmosphere plus H, A times rho times G times H. and this is for the water. So I just go ahead and multiply the A into both of these terms, and then I'm ending up to this. So this is the force which is pushing upwards. When we are in equilibrium, we also have a force which is pushing down, and this downward force is coming from the atmospheric pressure here plus the weight of the column of the oil. So this is P atmospheric times A, and then I have rho density. This is the volume of my oil, and then again multiplied with G. So when I have it in equilibrium, that means that the force which is pushing up has to be identical as the force pushing down with respect to the two magnitudes of these two vectors. So in equilibrium, I have F up equals F down with the magnitudes, and then now I'm putting in what I've got. So I have A times the atmospheric pressure on the water from here, and then A times rho water GH comes from the weight of this column here, is equal to the atmospheric pressure times A, comes from this opening, times the weight of the oil column. And then this line here is not going to move because the force pointing upwards and the force pointing downwards are identical, however, with opposite vector signs. Now, when I have this equation, there's a couple of things I can get rid of. This entire part is going to cancel with this part. So the both atmospheric pressures here are the same, so they are canceling. In addition, I have my A's and my G is going to cancel. The A here is going to cancel with this A, and the G is going to cancel with this G. And the H here, as I already discussed, is nothing else than the L here. And when I'm going now to have this equation solved for rho X, I get rho X is the density of the water times the height of that column here divided by the sum of these two distances. And when I put the numbers in, 998 kilograms per cubic meter for the density of the water times 135 millimeters divided by 147.3 millimeters. The millimeters are going to cancel, so this is fine with the units. And then I turned out that I get 915 kilograms per cubic meter. This is the density here of the water, which carries the unit forward because these ones are canceling. And this is what I expect also in the units for the density of the oil. And you see the oil here has a little smaller density as the water, and therefore you have the situation where the water is pushing the oil a little bit up asymmetrically from this half position here. Okay, so let's have a look how one can measure the pressure. And there is an invention which was done by Torricelli in 1674. And what Torricelli did, he was using a mercury bath here, so a vessel which was partially filled with mercury, and then he used this cylinder here, which is closed on this side. This is important, otherwise it won't work. So this is closed at this side. He completely filled it with mercury and then very quickly turned it around and pushed it down here into his mercury bath. And then what you see is that you basically have mercury flowing into the bath here, and it will stabilize at that point where the pressure here from the atmosphere is going to support the weight of this column of mercury. And then from the level here, you can go directly ahead and figure out what the atmospheric pressure is, because here in this area here, there is no mercury left. So that means the pressure here is 0 because there is nothing. There is nothing, there is no pressure. And so from this height here, which is then the height of the column, this is this height here, you can directly get the atmospheric pressure, which is pushing down here and supporting the weight of the mercury column. And then with this, because this P2 is 0, right? So we have P1 is P2 plus rho times G times H, the same equation as previously. P2 is 0. So you just get this one here, and this height here gives you direct the pressure at the atmosphere, which is supporting the height of the column. So this is a way to measure absolute pressures directly. And in this case, it's measured in millimeters. So be very careful. This is not an SI unit. And this is the same basically as P in Torricelli, because this was invented by Torricelli. Be very careful. This is not an SI unit. So another way in order to measure pressures is that open tube barometer. And this open tube barometer is going to measure gauge pressures. So what you've got is you have a tank with gas, and this is connected to a U-tube, which is open. So here you have the atmospheric pressure pressuring down. And then you have again a level where you have the gas, which is pressuring down onto this liquid filled manometer U-tube, and then you have the height here where you have the interface between the gas and the liquid. This level here all the way to the level where you do have the liquid atmospheric air, oxygen, nitrogen mixture here with atmospheric pressure. So what is important is again that the pressure here equals the pressure there, and that you can calculate now the pressure down here at level 2 by having the atmospheric pressure times rho times G times H, taking the rho of this liquid, of course, into consideration. And then again, as in the previous U form before, we have to know that the level, the internal pressure here at the level is identical. So we can write that the gas pressure, which is of course also here at the interface between the gas and the liquid. So P gas is nothing else than this P0 times rho times G times H. So if you want to know what the gas pressure is, and just using that height here, we can rewrite this equation. So P gas minus P0 gives us rho times G times H, and we know the density of this liquid. We know G, and we can measure H, and when we do this, we do get a gauge pressure. We get the pressure of the gas with respect to our atmospheric pressure, and this is what this part of the equation tells us. It's P gas minus P0. So when I do know how much P0 is, I can also calculate the absolute value, but this device here, the open tube barometer, is basically measuring the gauge pressure between the gas and the atmospheric pressure. Okay, let's have a look at another example with the gauge pressure. So the figure here shows a gauge pressure versus the depth of an object somewhere in a liquid. And then we are asked which of these liquids, A, B, or C, has the highest density. Okay, because this is a gauge pressure, we know that the pressure which is plotted here is rho times G times H. And H is the variable on which this graph is plotted to. So I do need to see what the slope is, and the slope of these three curves is of course rho times G. G is a constant, so therefore it doesn't tell us anything, and therefore the density is directly proportional to the slope of these three liquids. So when I have the highest slope, I have the highest density, and therefore A would be the answer when this would be a multiple choice question. The highest density of the liquid is the one represented by A. So liquid A shows the steepest slope and therefore has the highest density. Okay, so what we have seen in this lecture is what is a fluid, and this is a material which can flow and take any shape. It's both gases and liquids. We have to find pressure as the magnitude of the force vector applied to a particular area, and we have seen that there is pressure in a liquid which can be calculated as the pressure in a particular depth in the liquid equals to the, say, atmospheric pressure outside of the water tank, and then you have to add rho times G times the depth of the objects, uh, the depth in the water of the object where you're looking for the pressure at. And then we have discussed that there is absolute pressures where you really measure the pressure which is there, and that there's also a gauge pressure depending on which kind of device you're using to measure it. So the difference between absolute and gauge pressure is basically this pressure P0 here. This entire pressure here is the absolute pressure, and when you're going to look for a gauge pressure, you're typically only measuring this because you're looking for a pressure with respect to this one.